640 light-years away, a massive gas giant designated WASP-76b completes a full orbit around its host star in just 1.8 Earth days. At that extreme proximity, it operates as a planet-scale thermal engine. This tight orbit causes a phenomenon called tidal locking, a gravitational state where the planet's rotation rate exactly matches its orbital period. Because of this synchronized spin, one hemisphere faces a permanent stellar bombardment, while the opposite side stares out into a perpetual freezing night. This rigid geographical division acts as the stator of our planetary engine, the stationary housing that sets the stage for massive thermodynamic gradients to take hold. We know these exact conditions exist because of the physical data collected by instruments like the Very Large Telescope in Chile. Astronomers analyze this distant system using spectroscopy, a technique that measures how light interacts with matter to reveal a planet's exact chemical composition. This chart shows the specific wavelengths of starlight filtering through the exoplanet's atmosphere as it transits its host star. Hidden within those jagged absorption lines is the undeniable chemical signature of airborne iron. Finding heavy metals floating high in the atmosphere proves that the dayside environment contains enough raw thermal energy to completely overcome the immense density of iron. If we look directly at the substellar point on the dayside, the constant radiation pushes atmospheric temperatures well past 2400 degrees Celsius. This extreme heat triggers vaporization, the phase transition where matter absorbs enough thermal energy to change from a solid or liquid directly into a gas. The heat is so absolute that any iron present doesn't melt. It flash vaporizes, dissolving completely into a transparent atmospheric gas. The entire illuminated hemisphere operates as a continuous furnace, aggressively breaking down base elements for transport across the planet. Once the iron is suspended as a gas, it requires a transport mechanism to escape the dayside furnace. The system relies on a massive thermal gradient, the physical rate of temperature change between the blistering day and the freezing night. The superheated gas on the dayside rapidly expands, creating a severe high-pressure zone that pushes violently against the compressing cold gas on the night side. This relentless pressure differential drives planetary winds across the equator at 11,000 miles per hour, dragging the iron vapor along with them. These supersonic currents act as a continuous industrial conveyor belt, forcefully feeding the vaporized metal straight into the dark hemisphere. The transport cycle hits a physical wall at the exact geographic boundary separating the two hemispheres. This border is the terminator line, the strict dividing zone where the star's illumination abruptly ends. The millisecond the iron gas crosses this threshold, it encounters a violent thermodynamic shock, plunging into a sudden temperature drop of over 1,000 degrees. The terminator line acts as the absolute trigger for the engine's final phase, forcing the vaporized metal to react immediately to the freezing void. This sudden temperature collapse forces condensation, the physical process where gas loses thermal energy and reverts into a liquid state. Stripped of its heat, the transparent iron gas instantly clumps together, forming heavy, glowing teardrops of liquid metal high in the atmosphere. Gravity pulls these droplets downward, resulting in a continuous, violent rain of liquid iron plunging into the nightside abyss. WASP-76b operates strictly under absolute thermodynamic laws. It functions as a rigid, self-sustaining industrial smelter, continuously vaporizing, transporting, and condensing heavy metal across a planetary scale.